next discussion about light wave will be about single slit diffraction or single slit interference. The definition of wave interference is when multiple waves overlapping at a single point. So when we have a single slit, how can it produce multiple waves that could overlap? When we have a double slit and there is a wave passing through the slits, they spread out and they can overlap, so interference can happen. We have destructive and constructive interference. So for a single slit, how do we explain this? Why do the waves spread out at a whole? Why does a diffraction happen? And the answer is the key to single slit diffraction. We have something called Huygens principle. Huygens principle states that every point on a wavefront can be considered as a source of wavelets that move outward at the speed of the wave itself. For example, here I have a plane wave and we have several points on the wavefront. Each of these points is the source of a spherical wavelet, and the wavefront at a later time is tangent to all the wavelets. So if you have a wavefront coming in here, a wavefront coming in, you can treat every point on this wave as a source of another wave that spreads out spherically, and each point is the source of another wave. If you add this up, these are going to interfere with each other constructively and destructively in a way that just gives you this same wave front right back. If you let every point on this wave be another wave source, it will just add up to another wave front here. Diffraction happens because the wave was already diffracting. Every point was doing diffraction. When there's a barrier, the waves here are blocked. Only this one here spreads out, and then this one down here spreads out. All the rest of these gets blocked because there is a barrier here. So they're not going to interfere with these points here. We will just see this spreading out. These ones spreading out. So it was always diffracting, only we only notice it when there is a barrier. If we have a wave incident on a single slit, every point is the source of another wave. So this point is going to start spreading out. This point, this point, this point. When we have a single slit, we really have many sources of wave here. Some of them are blocked, but these sources of wave interfere with each other so that there will be big bright spot in the middle, and the pattern on the screen will be like this. When we see the pattern exaggerated, this is this single slit, and this is the light ray, and we will see the pattern on the screen will be like this. There will be a big bright spot in the middle. Here I have a single slit of width D, and the distance from this single slit to the screen, we call this L, and I have that many points as the source of wave, and I will draw the path of this ray coming to that spot there, and then from this coming to that spot I have this difference in path difference, which is equal to d over 2 times the sine of theta, because if this is d, then there will be d over 2 here. We can see it clearly here. if I have the width of the slit to be d, then this is d over 2. So this path difference here will be d over 2 times the sine of theta using geometry and simple trigonometry. And then for destructive interference or dark fringes, the path difference must be a half wavelength, 3 halves wavelengths, 5 halves wavelengths, and so on. So we have delta p, or the difference in path, to be d over 2 times the sine of theta. It should be equal to lambda over 2. Then we can formulate this and it becomes d times the sine of theta equals n lambda, where n is 1, 2, 3, and so on. And the sine of theta, because the distance L, the distance from the slit to the screen, is very far, so that the sine of theta can be equal to the tangent of theta. It is equal to y over L. So we have this equation for dark fringes, d times y over L equals n lambda. So this is for the dark fringes in single slit diffraction. For bright fringes, what about the constructive points? Usually, we only have to find the location of the destructive points for the single slit diffraction. So the problem will be about dark fringes. But if we want to find to find the formula to formulate the bright fringes, we have to notice that the central bright fringe for single slit diffraction is very wide. It is about twice the width of the other fringes. So the distance from the central bright fringe to the first dark fringe here will be lambda L over d. Then the width of the central bright fringe is 2 lambda L over d. So the distance from the central bright fringe here to the first bright fringe will be 1 plus a half lambda L over d. So we can formulate the bright fringes to be d times the sine of theta equals n plus a half times lambda, where n is equal to 1 to 3, and so on. So because the sine of theta can be written as y over L, so we have this equation for the bright fringes of single slit diffraction, and this is n, the integer. Remember here that d is the width of the slit. So I can summarize this in a table. I have 3 cases. For the Young's experiment, double slits, and the diffraction grating, multiple slits, the bright fringes or maxima is given by this formula: d times the sine of theta equals n lambda. d y over L equals n lambda. For the Young's experiment, d here is the distance between the 2 slits, while for diffraction grating, d is equal to 1 over n. d is the width of the slit, or 1 over the number of lines per unit length. For the dark fringes, or minima, d times the sine of theta will be n minus a half times lambda. And for the single slit, d times the sine of theta equals n lambda will be for the dark fringes. Yeah, for the bright fringes, it is d times the sine of theta equals n plus a half times lambda. Yeah, remember here that theta is the angle between the nth order of bright or dark fringes to the central bright fringe. Now, I will give you some example problem, page 196, number 3. Monochromatic light of wavelength 5890 angstrom is shown on a single slit of width A. Determine the width of the slit to create first bright fringe at deviation angle of 30 degrees. Here, this is the bright fringe. Yeah, so I can use the equation of d times the sine of theta equals n plus a half times lambda. The lambda is given, the theta is 30 degrees, and n is 1 because this is the first bright fringe. So I can calculate d times the sine of 30 degrees equals 3 over 2 times the lambda here, and d is 1.767 times 10 to the minus 6 meter. If you want to convert it to angstrom, then you have to multiply this by 10 to the power of 10. Next is the more problems, page 198, number 6 and 7. Number 6, monochromatic light of wavelength 4000 angstrom is incident on a single slit of width 4 millimeters. The distance from the screen to the slit is 1 meter. We want to calculate the distance between two adjacent bright fringes captured on the screen. Of course, for two adjacent bright fringes, we can use delta y, which is equal to lambda times L over D. It is the same as the previous formula for the double slit experiment. So we can calculate this. Lambda is 4 times 10 to the minus 7 times 1 meter over D. D here is 4 times 10 to the minus 3, yeah, 4 millimeters. So delta y is 10 to the minus 4 meters. The distance between two adjacent dark fringes captured on the screen will be the same. Delta y equals lambda L over D, so we will get the same result. See the distance from the second dark fringe to the central bright fringe. Remember that for dark fringes, for the single slit, the equation is this one, d y over L equals n lambda. In this case, we want to find y, distance from the second dark fringe to the central bright fringe. So y2 equals 2 lambda L over D, 2 times 4 times 10 to the minus 7 times 1 over 4 times 10 to the minus 3. It is equal to 2 times 10 to the minus 4 meters. The distance from the third bright fringe to the central bright fringe, we use the equation for the bright fringes, n plus a half times lambda L over D, and n is 3, third bright fringe. So we have 7 over 2 lambda L over D, and the result will be 3.5 times 10 to the minus 4 meters. And then we want to find the distance from the bright fringe to the nearest, not bright fringe, but dark fringe. So this is a half delta y, and a half delta y will be a half times lambda L over D, and that will be 5 times 10 to the minus 5 meters. And then the distance from the third bright fringe to the second dark fringe. I would like to draw the screen here, and then I have this central bright fringe, and then I have here first dark fringe, first bright fringe, and then the second dark fringe, second bright fringe, third dark fringe, and then third bright fringe. We want to find the distance from this third bright fringe to the second dark fringe here. So from the third bright fringe to the adjacent dark will be a half lambda L over D. So this one will be 1, 2, 3. 3 times a half delta y, yeah? So 3 times a half lambda L over D. It will be equal to 15 times 10 to the minus 5 meters, because previously we have calculated a half lambda L over D, or a half delta y, which is equal to 5 times 10 to the minus 5 meters. That is the distance from the bright fringe to the nearest dark fringe. So this is a half delta y, half delta y, a half delta y. We have 3 over 2 delta y. The next number is number 7. In a single slit experiment, the distance from the slit to the screen is 180 centimeters. That will be L. The width of the slit will be D. The separation between 7 dark fringes, I will draw this. This is the first, second, third, fourth, fifth, sixth, and 7th dark fringes. So the separation between 7 dark fringes is 7.2 centimeters. We have 1, 2, 3, 4, 5, 6 delta y. So 6 delta y is equal to 7.2 centimeters. 7.2 times 10 to the minus 2 meters. We want to find the lambda. Delta y is lambda L over D. Yeah, so we can substitute L and D using the amount given. 1.8 meters and 9 times 10 to the minus 5 meters here. And lambda can be calculated to be 6 times 10 to the minus 7 meters. That's all. If you have any question, you can ask, and you can do yourself from your physics textbook the example problems that I have discussed, number 3, and then the more problems, number 6 and 7. Please do it yourself in your book and make sure you understand. And then the multiple choice question, page 202, number 7 until number 12. Please do it as your exercise. That's all for today. I hope this video is useful. Thank you.